going to present you a work that it has been prepared by Professor Police and myself, and is concerned with an isotropic disk loaded by a parabolic distributed pressure. Actually, this work is, of course, a theoretical work, pretty theoretical work, and it's a first step in allowing to say an assessment or decision upon the applicability of the Brazilian disk test on anisotropic disks, and particularly, as we will see, transversely isotropic disks. Starting from the material, I would like to remind you that here we can see a transversely isotropic body. We are going to use the term transtropic for brevity. And in that, such a body is a body which, when it's homogeneous, at this point of its mass, possesses parallel planes of isotropy. And what we are doing is to cut out the specimen, a cylindrical specimen for this block, and in such a way that the cross-section of the disk has placed normal to the planes of isotropy. And then we subject this disk in this parabolic pressure, and this is the problem we are going to solve here analytically. Of course, this configuration make us to consider of the well-known Brazilian disk test, the experimental setup of which we see in this picture according to the International Society for Mechanics standard. Of course, we would have, in the present case and for the present problem, perhaps a flat loading platen. For those who are not familiar with this test, the Brazilian disk test is the most popular alternative of the direct tension test for the determination of the tensile strength of brittle materials such as rocks. And according to this test, which actually has introduced some 70 years ago independently by Garnier and Casaba, instead of implementing the tensile test, we compress the disk between these jaws, and we expect the maximum tensile stress to appear at the center of the disk, which in combination with a perpendicular radial pressure leads to the split out of the disk into two parts, so we obtain the tensile strength of the material as a function of the externally applied load level. And this is exactly the problem we are going to solve here, the Brazilian test, when our disk is made of a transtropic material. Of course, this problem is not a new problem, has already been dealt numerically and experimentally, and also there is an analytic solution given by Xadaktilos and Kathlis when the disk, when the externally applied load is uniformly distributed along two predefined loading arcs. And however, I would like to mention that there are only few works in this area when we consider the Brazilian disk with a transtropic disk. And coming on to our work, the advantages of the present solution and the novelty lies to the fact that we are going to consider a parabolic distribution of radial pressure instead of, perhaps, as we have seen in the previous slide, a uniform one. Since the parabolic distribution is much closer to reality, recall that when two cylindrical bodies, as here the jaw, the curved jaw, and the disk come into contact, then the compression along the interface is described by an elliptical law, actually. Here, of course, we consider a parabolic one, in order to avoid some extra approximation in the solution, since an elliptical law here for the distribution will lead to elliptic integral, so we want to avoid the elliptic integral, so we consider statically equivalent, very close to the elliptical one distribution. And the other advantage of the present solution is that we don't consider a predefined loading angle, but as we will see later on, this loading arc will be obtained as a function of course, the load level, but also as a function of the elastic properties of the material. And as we will see next, we are going to relate the present problem with a contact problem, thinking that contact first realized in the unstressed condition along a point or along a single generator, along the thickness of the disk, and by gradually increasing the external applied load, finally we take a finite contact arc. So we are going to obtain this contact arc and not predefined, not defining a priori. But I will comment on this in more detail later. Now, in order to solve this problem, we are based in this milestone books of Lechnitsky. Actually, this is not the actual, the real hardcover. From this book, we are going to take the basic elements of bodies, of anisotropic bodies, whereas from this second book, we are going to adopt the general formula of Lechnitsky's complex potentials for our problem. So, we consider our disk line in the Z complex plane, and these are the coordinate reference with the origin at the center of the disk and XZ plane parallel to the planes of isotropy. The external applied load will form an arbitrary angle phi0 with respect to the planes of isotropy, whereas this angle omega 0 will describe the extent of the loaded ring. Actually, the extent of the loaded ring is 2 times omega 0 multiplied by the disk radius r. And for the specific choice of the Cartesian reference, in a general case of heterostropic material, these are the generalized Hooke's law related in strains to stresses through these engineering constants. In our case, epsilon, ni, and g will represent the Young modulus, the Poisson ratio, and Sierra modulus in the planes of isotropy along the strong direction, the so-called strong direction, whereas the respective quantities with primes will represent the corresponding elastic constants normal to these planes, the so-called along the so-called weak direction. And for our case, where the problem is plane, actually the external plane load is within the disk cross-section, and the deformation is plane, since the cross-section of the disk is a plane of elastic symmetry because it's perpendicular to the planes of isotropy, so the cross-sections remain plane also after deformation. We have a pure plane strain, and in that case, the equations characterizing the elastic equilibrium of the body boil down to this set of expressions: the equilibrium equations, generalized Hooke's law, the one compatibility equation, the analog of Beltrami-Mitchell in terms of stresses only, the boundary conditions, all given in terms of these engineering constants. And as usual, the equilibrium equations tell us there is a stress function related to stresses through this equation. So introducing these equations into the compatibility equation, we take the generalized harmonic equation, and this is its characteristic equation, and these are the roots of the characteristic equation, the so-called complex parameters, purely imaginary numbers. The two of them are complex conjugate of the other two. And by the end of these complex parameters, we can perceive these complex arguments, the so-called complicated or generalized complex arguments, and in turn these two functions, phi1 and phi2, where it's actually the complex potentials of Lechnitsky, in terms of which we can define the real stress function f. So we introduce these complex potentials in the previous expression we have seen for stresses. We obtain stresses, and here are the boundary conditions for stresses in terms of this complex potential. So once we have obtained these complex potentials, then we have the full stress field on the disk's cross-section. And these are the complex potentials. I have told you before, we take from Lechnitsky the general form. So introduce them into these expressions, expanding the right-hand sides in Fourier series form, and combining coefficients to finally obtain the coefficients of this complex potential, so we have the full stress field of the disk. We don't have written down here these expressions are very lengthy, and actually it's not need to write them down, since by the end of the computers nowadays, softwares like Mathematica or MATLAB, we can just program them and take stresses at any point of the disk with great accuracy. However, if I have written down this expression, we will see that any of the stress components, these stress components in the plane state, will multiply by term PC, which is the altitude of the parabolic pressure, the maximum value of the parabolic pressure, and the contact angle omega 0. Actually, the contact angle omega 0 is in all these constants we can see here. And now I'm coming to the next advantage of this solution, that is to obtain this contact region, this contact arc, and also the altitude PC, as I have told you before, PC of the parabolic pressure, in terms of not only the loading level, but also on the elastic properties of the material. In order to do this, we resort to these expressions. We have obtained Professor Goulis in the case of when an isotropic disk is compressed against the jaw of International Society for Mechanics. Of course, in that case, when the disk is isotropic, we don't see these angles phi0 here, since then the angle phi0 is meaningless for the case of an isotropic disk, since in an isotropic disk all directions, independent from the orientation with respect to x-axis, are elastically equivalent. So what to do here is to modify this expression in order to adjust our case, and to do this we start from this case when the external applied load is parallel to the planes of isotropy. Then we can obtain easily from the data of the problem and the symmetry of the matrix of the Zerl-Hooke's law, the Poisson ratio corresponding to the dilatation normal through this compression is given by this expression. Whereas in the case, in the other limiting case, when the external applied load is normal to the planes of elastic symmetry, then straightforward from the data we have this Poisson ratio equal to μ prime. And reasonably, I think we have simply assumed that in the case when the external applied load forms an arbitrary phi0 with the planes of isotropy, then the dilatation along this direction will be described by the aid of this Poisson ratio. So, assuming our disk as if it were instantly an isotropic one, we introduce this knee in this expression of Skelisvili, in case of an isotropic disk, of course, and for plane strain conditions. And then in this K capital, and then in these expressions for the contact angle and the altitude of parabolic pressure. So we have the altitude of parabolic pressure and the contact angle for any orientation and load level of the external applied load. So we introduce all these findings into the preceding formula for the stresses. We obtain stresses at any point of the disk. And now I'm coming to some results and conclusions. Here we have used this formula for stresses, and of course, though mathematical, the work we have used real material, serpentinium schist, and nominal values. Actually, this material has been taken with elastic properties from a work dated by Parra and Naurato, dated back to 1973. These are the elastic properties, and I think here I have used an external applied load of 15 kilonewton. And we have first we have concentrated we have focused our concentration at the center of the disk at this point, or this, as I have told you before, is supposed to be the point of the onset of failure, according to the Brazilian distress. And here we have plotted the ratio of the normal stresses, the radial over the hoop one, versus the angle phi0 as the external applied load rounds. And we see that contrary to the case of the isotropic disk, where this ratio is constantly equal to 3, here we see that this ratio varies from 5 to almost 2 from as the loading angle changes. And this significant difference is first point of questioning about the applicability of the Brazilian disk test. And for many investigators, in order to draw safe results from the test, you have to have a ratio somewhere around this value 3. And here we see that this is not the case. And remaining at the center of the disk, we have also plotted the ratio of the transition over the Hooke stress again against phi0, the orientation of the external applied load, where we see again that this ratio, actually in the case of the isotropic, this ratio is 0, due to the fact that there is no stress, that there is not shear stress at all at the center of the disk. But however, here we see that this ratio attains a comparable value, especially at 30 degrees, which is also another evidence that the mechanism of failure at the center of the disk, if is the critical point in our case, is not an easy but a complicated situation. And we also, finally, we have plotted stresses along another locus of interest in the case of the Brazilian disk, along the loaded diameter from 0 to r, and where, apart from a first similarity, we have plotted all three stress components for 3 different phi0 values. And here is also an embedded figure where it's actually a magnification of this area and this, of course. And apart from a first similarity we can detect between the isotropic and the heterotropic disk, we see here that there are some differences, significant differences, mainly like the fact that even in that case we have a non-zero shear stress all along the loaded radius, which maximized somewhere under the loaded platen, somewhere here. And this is also another evidence telling us that the mechanism, the critical point of the Brazilian disk is not an easy task to obtain in case we have a transtropic disk, since we have to recall that sometimes, many times, failure occurs instead of the center of the disk somewhere here under the loading platens. So, to conclude, we have obtained a solution which gives us the chance to have the full stress field, and by the end of this formula we can have an overview of the stresses everywhere on the disk, and of course from the findings we have from the center of the disk and for this plot we see that the failure mechanism perhaps is more complicated in the transtropic disk, and certainly is completely different from the isotropic one, and we can't draw safe results unless we use or apply first some failure criteria to identify the critical points, and of course to supplement our work with some experimental results or numerical perhaps findings. And finally, to conclude, I would like to express our acknowledgements to National Technical University of Athens for support, and particularly I would like to express Professor Kokoulis and my gratitude to ESI's Executive Committee and scientific team for deciding upon the value of our work and waive the fees. We are very grateful, and it was all not only a honor but a help in these days we are all going through. Thank you very much for your attention.